Thank you all for coming, and welcome to Friday and lecture 7. So today we're going to talk about graphs, charts, visualization in general. But as usual, some basics. Homework 3 will be released later today. The staff, our wonderful core staff, have made lots of sort of helpful materials for you. And one of them is a primer on arrays. That's on Ed. They asked that you be aware that next week you're going to have to log on to your berkeley.edu, your CalNet account, to access the office hours queue. And I don't have the details of the instructions, but they'll be posted on Ed. The office hours queue works using an application called OK. That is a Berkeley written application, started out with CS61A, and we actually used to use it for auto grading, though we've switched to something else. But don't worry if that app asks you to log in via your CalNet. It's it's safe. It's a Berkeley thing. So if you have logistical questions, it may be worth taking a minute to ask them now. I almost certainly will not be able to answer them, but perhaps the GSIs will. No, wonderful. Feels like the class is getting into full swing. So we are at Friday today, and we're going to talk about visualizations. You saw on Wednesday that we had started working with large sets of numbers. And even though they were very organized sets of numbers, it was still, they made your head swim when you looked at lots of numbers. And at the end, we drew a graph. And that graph told us very quickly a story that took us a little while to tell by just looking at the numbers. And so today we'll talk about visualization. And I hope you will find that the code, how to actually draw a visualization using tables, is rather simple. So what we're going to be focusing on now is the principles of visualization, interpretations, and things that you should look for when you are about to create your own visualization. And it's one of these sessions where almost everything that we're going to talk about, in some sense, you have seen a million times in newspapers, in books, and so on. But I hope that you will be able to look at it now with new eyes and realize that there are things to notice which you perhaps may not have thought to notice before. So we'll start out with some fundamentals before getting into code and looking into drawing our own graphs. We'll start out with some fundamental principles of visualization. And I'm going to start you off with what not to do. Take a look at this thing. That appeared as a visualization in the Washington Post in the 1970s. And I think you'll agree, without even looking at the details, that it makes your head hurt. There's just a lot going on in that picture. It is the attempt is to compare the incomes of doctors. Those are in the white bars and represented by each of these doctor-looking silhouettes, with the incomes of other professional, technical, and kindred workers, all male. And those are these people represented by, I am actually not quite sure what, maybe the tops of the heads of these silhouettes down there. And there's just far too much going on in this visualization. Do we really need a doctor's head on the top of every single bar? So it's fun to be able to just draw such things, but just because you can draw something, you shouldn't necessarily draw it. So we really don't need all of those heads. But notice how our eye immediately gets drawn to the heads. So our eye immediately gets drawn to the vertical. But what I would love for you to do there, thank you, Mukt. Always, always, always start with the horizontal. Take a hard look at that horizontal axis. By the way, make a note somewhere in red if possible. I will always start by looking at the horizontal axis. What are you seeing? Mukt and Dilan have already noticed something. You're saying years, very good. Years, 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 yeah. Okay, now look at the numbers. Not evenly spaced out, not consistent. You have 1939, 1947, 1951, 55. There's just 65, 67. The physical spacing between successive numbers is the same, but these are actually numbers on a number line. And that mathematical relation between them has been just sort of violated. Now, the minute you violate math in one part of your diagram, it's going to be really difficult for you to give a consistent interpretation of anything else. Okay, so that horizontal axis that you see, where basically the numbers are being treated as artwork, as somebody has said, that's called a rubber band axes, that you're stretching them out differently at different places. Yes, exactly. So Sri has noticed that intervals are not constant, which messes up the slope scaling. If you look at the lower graph here, it's sort of linear. If you look at the upper graph, it also looks linear, except if you actually do what you ought to do, which is draw this simply like this, then you see something quite different. So this is a classic of what not to do, and so it has been corrected by many people. This correction is by Rossi Haka. This is very clean. Both of the variables are quantitative, so there's years which have a certain fixed spacing. It is very easy to tell a story using this graph. Both the axes are numerical, clean, and yes, exactly, Lincoln says it's prettier. It did not need all of that embellishment to be visually also appealing. And so this tells us a few principles. Why is there a dashed line? That's a very good question. There is a dashed line because if we go back to the previous, if you squint right here at 1947, right, what you're seeing, if you really squint hard, that is an NA. They did not have the data for 1947 for these technical and other kindred workers. And therefore, they skipped the 1947, they joined the dots 1940 to 1950, which is where they had data. Okay, so yes, as somebody used the word minimalist somewhere in the chat. Asha, thank you. Exactly, less is more. So a good practice is to minimize decoration. It is known as chart junk. This was a phrase coined by one of the premier visualization experts, Edward Tufte. I'll give you a reference to his book in a bit. So minimize decoration. These days we can use color. It is very tempting to use all kinds of colors and jangly colors, but really try to minimize. Color can be used with great force, but overdoing anything can obfuscate your message. It can hide the message that you're trying to give. Worse, it can give a wrong message. Okay. If the data are numerical, please, then preserve the relative distances between them. What about color for colorblind people? That is a very, very good question. Red and green are bad colors to use. So thinking about that is a very good thing. And let me just point out a book that you should get hold of if you can. And then I'm going to show you, Gillian, this may address your question a little bit as well. I'm going to show you what is considered one of the greatest visualizations, perhaps of all time, data visualization. And that is this map of Napoleon's Russian campaign, which was 1812 to 1813. The map was drawn by a Frenchman called Minard in about 50 years later than that. Before I go into details, do you remember that when I first lectured, was lecture 2 on Jon Snow, I also showed you his visualization. That was in 1854. And these, yes, exactly, the water pipe graphs, and he had little rectangles which he was using to mark the deaths at each address. And these people were all drawing by hand, right? But perhaps because they were drawing by hand, which, and we'll talk about the map in detail, perhaps because they were drawing by hand, they had to think very carefully about exactly what needed to be drawn, because they didn't have the facility necessary to do all kinds of complicated things easily. So let's talk about what's being displayed here. So the Napoleon's army set out from the middle of Europe here at the left edge of your graph. The sort of light brown path is the advance to the right end, which is Moscow. The width of the path represents the number of soldiers that were there, the size of the army that were there at that point. Okay, now this is placed on a map. So you're seeing because it is a map. Yeah, exactly. So latitude and longitude is being preserved. And so they went to Moscow and, you know, things weren't good. The black portion is the retreat. What happened to the soldiers? The Russian winter happens to the soldiers. Yes, so this tells a very painful story. And you can see that, for example, these people, there's a little branch that took, can you see my cursor? Yeah, okay. So there's this little branch that took off, that didn't actually go to Moscow, right? And then towards the end, yes, towards the end, they came down and joined their fellow soldiers who were in retreat. So you can see the widening here. But then what happens? Well, it's November. They cross a river and not in boats. You can see what happened to those poor soldiers in the river. And as Ravpreet points out, the bottom panel has a lot more information. The bottom panel shows dates, and this will help. This is November, and so in Moscow, they were leaving Moscow in October. It's a little easier to read if you have a little bit of French. But anyway, it's November, and so November, and this is cold, and then you have minus something degrees, minus 20 degrees, minus 30 degrees. That's cold. So this graph, so let me actually pause for a second and take questions about the graph. It was a stunning summary of the information, where the light brown part, Pooja, represents the army advancing. It was a very stunning choice of how to represent a lot of information in a simple picture. The top left, I think, is portions of the army were wandering off to other places. Light black line on the, oh, this axis, I am not sure. Actually, my eyes are not good enough to read the French, but I will read it later and I will send it to you. Maybe somebody else can do that. The point is that this picture represents 6 variables. The number of soldiers, latitude and longitude, direction, dates, and temperature. And so you will find that many people who work in visualization, many statisticians have a print of this on their wall. The brown and black have different widths because the widths represent the number of soldiers, and unfortunately many of them died. Right, the black is the retreat. There weren't that many soldiers left at that point. Okay, so when you are trying to do a visualization, keep Minar's map in your mind and try to have that as a goal. Okay, so at this point, we should try and make some visualizations ourselves. And so I'm going to talk about statistical data types, and I include the word statistical here because we've already talked about Python types, and this is different. We're just looking at variables. Now, what's a variable? A variable is what we've been calling an attribute. So on a single individual, we measure different attributes. If you look at a particular attribute, it will vary, its values will vary across individuals, so it's called a variable, and there are two kinds. Well, commonly, two kinds, and why cannot? Okay, so there is a quantitative variable which is measured numerically, and you've had two examples in the previous lecture, age and population size, and then there are categorical variables. These are variables that are not numerical. They're just, it puts individuals in a category. For example, you can have unordered categories. So that for each individual, if you ask them what's the color of your shoe, then you'll get, brown, black, red, white, whatever. And those are categories, but there's no particular order to them. Or you can have a ordered categorical variables. You have many surveys where you have to fill out, I think even in teaching evaluations, not satisfied, satisfied, very satisfied, or not effective, somewhat effective, etc., etc., etc. These are categorical, but they have a natural order. Now, these are quite different because the quantitative ones are actually numbers and you have to preserve the math. The others, well, zip codes, I would consider them to be a categorical variable. I'm actually not sure about order there necessarily. And so you've brought me now to variables that look like numbers, but they're actually categorical. So you've seen one already, the sex codes were 1 and 2. Those were actually not numbers, they're just labels. And the point is that doing arithmetic with these numbers does not make sense. So if you use 1 for Berkeley student and 0 for not a Berkeley student, then 1 plus 0 divided by 2, I don't know what that is. Okay, so if you use, on a scale of 1 to 5, rate such and such, well, okay. If you use 0 for not satisfied, 1 for satisfied, and 2 for very satisfied, distances actually are rather questionable. Right, so in math, 1 minus 0 is the same as 2 minus 1. But it is not clear whether the difference between satisfied and very satisfied for one individual is the same as the distance between not satisfied and satisfied. And why don't we just take for as an example, the attempt to assign numerical grade points to letter grades. Right, so we've got this letter grade scale that goes up to A+, right? So what's the numerical value? What's the grade point for A+? 4. What's the grade point for A? Also 4. What's the grade point for B+? Anybody? 3.3, and what's the grade point for B? 3.0. You see, so so B plus differs from B, but A plus does not differ from A. Somebody made these decisions, right? And people do arithmetic. GPA, this is used everywhere. You put it on your resume. Grade point average. There's arithmetic being done with this. If you want to start a rip-roaring argument among all your friends, be provocative and suggest, we should perhaps use GPM, grade point median. Half my grades are above this, half are less. Everybody will hate you, I promise, and the world will end. We should not mess with grades. But I just want to point out these things that we take for granted. They come from somewhere and somebody's made decisions, and decisions can and perhaps should be questioned. Okay, so what we'll do is we'll start by looking at quantitative data. And there are two kinds of plots that you are, I think, used to seeing. One is a line plot and the other is a scatter plot. And now I'm going to try a demo. Right, run the cell. Okay, it's Friday. We're going to the movies. Every single example today is going to be movies. So here is a table that shows by year up to 2015. And I know we should update this data set. The number of movies that were released that year in the United States, the total gross dollar amount in millions, and the number one movie, that is the one that had the largest gross amount. So that's a table, and it has 36 years represented. Now, years are sequential. It would be nice to see how, perhaps the number of movies changed with time. And so we will draw the line plot of that. And the call is table name dot plot, and then label label of the X variable, and then the label of the Y variable, which is, what is it called? Number of movies. Okay, I have to be careful of my uppercase and lowercase. And you have that. Okay, easy call. So if you follow this, I'm actually not sure what happened with the data here, but in general, it's kind of going up. Look at this dip here. This is which year? This dip right here. Which year? 2009, actually, because 2005, 6, 7, 8, and it's 9, because it's the year after the crash, right? When people had no money, fewer movies were made. And so let's look a little bit at just year 2000 onwards. And I'm sorry, I couldn't resist an awful pun. These are 21st century movies. So I'm calling the table Century 21. And that's these films. And some of you will recognize some of these friends as old friends that you have watched. Okay, so what I'd like to do now is look at the total gross income as a function of the year. So it's this table now. Plot the x-axis is going to be year, and the y is going to be the gross income, and so that looks like that. And there's a couple of things to note. The first thing I note is that I hate this. For some reason, it's giving me half years. It's somehow there's an odd number going on with the label. So I'm about to do something here that you do not need to do. We'll do it for you. I'm just going to mess with the X label. Sorry. Okay, let's run that again and see if that, okay, that's much better. Okay, so what we're looking at, I'd like to look at 2008, right? So 2008 is right here. Look at 2009, it's here. Is that a dip? That's not a dip. That's not a dip. There were fewer movies made, but there is the amount grossed by the movies was higher. Lydia, exactly. People didn't have money. They went to the movies. They couldn't afford restaurants. They couldn't afford travel, but they did want entertainment. People were miserable. They went to the movies. Charlie, the semicolon after the X lim just stops some unnecessary printout. You can try it out and see what happens. Yeah, exactly. The economy was sad, and so people went to the movies more. Okay, so a simple little line graph tells you stories. Now, one of the things I want you to notice about all line graphs is if I look at this, the way it has been drawn, it looks like the rise is very steep. And also it looks like, oh, if I look up to about 2007, from 2000 to 2007 and then 2007 onwards, it looks like the number has almost doubled, except that we're starting not at 0, we're starting at 7,500. All right, so we've already said that we will start looking at all graphs by looking at the horizontal axis. Look at the horizontal axis first. If it's numerical and you're looking at steepness and so on, look at the vertical again and look especially at the start. Because if I now force this to start at 0, which I'm not going to ask you to do, but you can see parallel in the code. How far up does it go? Let me just go up to 1200. 12,000, sorry. Okay, let's run this thing and see what happens. Look at that. Suddenly looks much flatter. Yeah, because your starting point is 0 and the picture is not as dramatic. It is still true that the difference 2000 to 2007 is comparable to the difference 2007 onwards, but it's not a doubling. All good? Questions? Okay, so when do you use a line plot? Which is better? Well, you decide which you're going to draw, but you just have to make sure that you interpret correctly. Right? When you're reading somebody else's graph and it's a line graph, always look at the y-axis to see are they starting at 0 or not, and that will affect how you interpret distances and absolute quantities. Should you always, you know what, I actually don't think there's anything much wrong with this graph. What would be wrong is to say that there was a doubling in over 2 epochs. You just have to be careful that you are measuring distances from 7,500, not from 0. The point is that you observe things so that you interpret correctly. Okay, so when do we use a line graph? Typically when there is a sequential horizontal axis. And that's usually when it's, time, or sometimes it's distance. And it makes sense to think about sort of sequential behavior of the y-axis. But sometimes there are 2 variables that are numerical, but there is no natural sequence. And so we will start with another movie data set, which is called actors. And this has, for 50 well-known actors, I think this was roughly, 2016-ish data, for 50 well-known Hollywood actors, the name of the actor. Okay, this variable, the name of the actor, is a categorical variable. These categories are interesting in that they have exactly one individual in them. Still, the number of movies, which is a quantitative variable, the total dollar amount grossed in millions. Now, total what? Harrison Ford was in 41 movies up to that point. These 41 totaled this amount of money, 4,871 million. The average per movie was 118.8. And so this is redundant information because in some sense you can calculate it, right? You can take the total gross and you can divide by the number of movies and you should come up. If you take this 4,871 divided by 41, you should come up with this 118.8. It's average per movie. So let's do that at the bottom before I get to the rest of it. So if you take the total gross column and divide by the actors column, then you get exactly this average. And I actually like tables that give redundant information because it allows me to do the check. It helps me have confidence that I'm understanding the table correctly. Okay, now, this actor, so Harrison Ford's #1 movie was Star Wars: The Force Awakens. What does that mean? Of their 41 movies, this was the one that had the highest gross. All right, so this 936.7 was the highest among the grosses of Harrison Ford's 41 movies. Questions about the data? I honestly cannot now remember how the actors were chosen. Okay, so what we're going to do is look at the relation between the number of movies that these actors are in and the total gross income. And there's no natural sequence because the individual is the actor and the actor changes from point to point. So what we're going to do is draw a scatter diagram, and the call is just like plot. Table.scatter, label of the x-axis variable, label of the y-axis variable. Okay, now, so you get what we're going to refer to as a cloud of points. So let's understand what each point represents. Each point represents what? A row or a column? How many points are there? A row. There is 1 point for every actor. Each point represents an actor. On the x-axis, there is the number of movies of the actor, and the y-axis is the total gross of those movies. Okay, and so let me look at this actor here. This actor was in a lot of movies, but the total gross is not that much. Let's take a look. It's Robert De Niro. And oh dear, Robert De Niro's #1 movie, look what it comes out to be. Anybody seen that? Yeah, well, it's funny, right? And he's a funny guy. But I mean, Robert De Niro, how about, Taxi Driver, Raging Bull? Yeah, he's a better actor than that. Yeah, however, we're just counting, what was the movie that made the most money for this person? And at that point, it was this one. So what I'd like to do now is look at the same thing, number of movies versus another variable, the average per movie. Have I got my uppercase and lowercase right? Yes, okay. Okay, that is interesting. So I'll do that in just a moment. Dilan, hold on. I will do something like that in just a moment. So you take a look at this graph. What is it showing you? I think it's showing you that the more movies an actor makes, on average, the less money they make. What do you think? Yeah, it's kind of showing you this is what it's called a negative association. All right, if we look up, this scatter diagram is moving upwards. So the larger number of movies is associated with a larger total gross. So that is that's believable. And so you have a positive association there. Here you're seeing a negative association, but everybody surely is looking at who, what, this, who is this person? Who is this person? So we have to do a where, right? And so what is interesting about this? Well, there are two things interesting. They have a very low number of movies. So how about, will that get them? Number of movies are below 10, will it get them? It'll get them. Okay, shall we see who it is? Let's see who it is. It is, dun-ta-da, Anthony Daniels. We all know who Anthony Daniels is. Do we know who Anthony Daniels is? You bet we know who Anthony Daniels is. We know who Anthony Daniels is. That's who Anthony Daniels is. It's C-3PO. It's the actor behind C-3PO. Okay, so Anthony Daniels, and now this is where we have to really pay attention to what is being measured. All right? No, sorry, not R2. This guy. So Anthony Daniels, what is being measured on the horizontal axis is the number of movies this person was in, right? And they didn't count, very small guest appearances or anything like that. They counted where the actor had a significant part. So this person and this actor appeared in the Star Wars franchise. Right? Now, every one of those was a blockbuster. So on average, the actors' movies made a ton of money. And that is why they are right here. They appeared in only 7 movies, but on average, those movies grossed, I don't know, what is it, 460 million or 450 million. Okay, so it's important to keep in mind not only what is it being measured, but on whom it is being measured, because on whom it is being measured has a significant effect on how you interpret your data. And it's important to keep in mind also is that this is not what the actors are making. This is what the movies are making. All good? All right, so I hope you agree that the code is rather straightforward. And it's the interpretation that's fun. Okay, so what I'd like to do now is let's see if we can summarize a little bit what we have. So these are your 2 calls that you've learned to make, and T stands for table as usual. And you use line plots for sequential quantitative data. If your x-axis is in order, you actually care about the sequential differences on the y-axis. And there's only one y value for each x value, which doesn't always have to be the case. You can have data with multiple y's for the same x. And if you have such a situation, you have non-sequential data that are quantitative, and you're trying to see what is the relation between these 2 variables, then the scatter plot helps you out. Sometimes you might draw a scatter plot and realize, oh, wait a minute, this is actually sequential. Let me draw a line plot. So mess around and see what gives you meaningful information. Okay, so we will now move to looking at the relation between a categorical variable and a quantitative variable, because there are many data sets, and that's the next one we're going to look at. There are many data sets which contain both. So this data set has some of the highest grossing movies. So the title is, of course, categorical. The studio in which the movie was released is a category. Each movie was released by one and only one studio, but multiple movies can belong to the same studio. Then there are the gross dollar amounts that the movie made. I think it's the domestic US box office. But Gone with the Wind is a very old movie compared to the Titanic, and $1 did not mean the same thing. So there are also the adjusted dollar amounts. And those are adjusted as, I think, they're $2016, if I remember correctly. And then you have the year in which the movie was released. And I think this is best viewed. So the point is that we have both categorical variables and quantitative variables, and we might be interested in which movie made how much money. And the minute we ask that, which movie is categorical, how much money is quantitative. So we read that. So these are the top movies in a bunch of years. Yes. So before we get to actually drawing charts, look at the data. You see these 2 columns, the gross columns, there are lots of digits there, and it is very hard, very, very hard to keep track of all of those digits. So for readability, we're going to do some data cleaning. All right, we are going to convert these to millions, and that's what I'm doing here. So this column of gross box office receipts, we are going to take that column, we're going to divide by 1,000,000, and then we are going to round to 3 decimal places. Somebody please explain to me, why am I using np.round and not just round? Because we are rounding each element of an array, right? So wonderful. And so we've done the same thing to the gross adjusted column, creating a array called millions adjusted, and then we augment our top movies table with these two columns. And so now you see these last two columns, the millions and the adjusted millions, are much easier to read. And so let's just look at, and this actually tells us something very quickly. You've probably noticed it already, that these movies are in a certain order. They have been sorted by the gross adjusted. Do you agree? It sure looks like it from these top 10. And indeed, that is true. And so we'll just look at the top 10. And so I'm calling it top 10 adjusted because it's top 10 according to adjusted millions. Okay, and so that's exactly, visually, that's exactly the same table, but this one has 190 more rows and ours only has 10. And so now what we are going to do is we are going to, for every movie, look at the millions adjusted. And I can see this is, okay, this is 900 million, this is about 1800 million. It looks like there's a factor of 2 there. But that's still hard to tell by looking at the numbers, how big are those sizes. So one natural thing to do is to draw a bar chart where there is a bar for each movie, and the size of the bar represents these adjusted millions. And so the call is table name bar H, because we are going to draw a horizontal bar chart, and I'll explain why in just a moment. And you provide the name, the label of the categorical variable, and then the label of the numerical variable whose sizes you want to see. And that looks like this. And what I'd like to do is take a few minutes just to look at this very, very carefully. I mean, it's a bar chart. You've seen bar charts since you were tiny, but it is time today to look at this thing carefully. First, why are we drawing horizontal bar charts? It's because the labels are long. And if you drew them vertically and your labels would either have to be written, yes, you can, but your labels will either overlap each other, or they have to be written vertically and they cannot be read. So we will invariably be doing horizontal bar charts. It's just easier to see what's going on. I think it might be just dot bar. I don't know. You check. Maybe one of the GSIs can help out here. I've forgotten. All right. So take a look at this and notice something, right? On the variable, the categorical variable is not ordered, right? Yes, they've been put in order according to the size of the variable, but in some sense, the movies themselves don't have any particular order. So somebody chose that order. With a categorical variable, you get to choose the order of the bars. Okay, so thank you, Charlie. Yes, just bar, not bar V. Okay, now look at these bars and just notice that these widths, they all have, so I'm going to call this long thing the length, and this the width of the bar, which is a little contrary, but bear with me. It will make more sense on Monday. You notice that somebody has decided that every bar should have the same width. Can somebody tell me why that might have been? I mean, supposing the Snow White bar, easier to compare, yes, because maintain homogeneity, but homogeneity of what? Just for visuals? No, Kelechi, I think it's more significant than that. Because the variables, okay, everybody's wandering around, accurate comparison of what? Okay, so what I'd like you to do is imagine, width shouldn't matter, Jackson, so I'm going to ask you to imagine something. Take the last bar, right? Snow White and the Seven Dwarfs. Yes, and think of making the width 3 times as wide, right? Same length, but 3 times as wide. What will your eye pick up? Lawrence has already said it, and I think so a number of people, your eye will pick up area as big. right? And then it will be difficult for you to quickly see, well, wait a minute, which one actually is more? There's no density. It's simply representing the number, right? But it is representing a number in a way that our eye can perceive very quickly. All right, so all other things being equal, what we're noticing is the length of the bar, and that is what is representing the amount of money made. So it actually matters that the bars have been chosen to have equal widths because our eye picks up area as big. When you draw a picture that actually has area, and especially colored area. Notice also that the gaps between the bars are all equal. Why is that? Again, it's an artist's choice, right? There's nothing, there's no actual numerical reason, but why do you think that choice was made? So it's also not distracting. It could be confusing, easy. Yes, Alex, thank you very much. So the movies don't look grouped for any reason, right? If say the gap between 10 Commandments and Jaws was 3 times as big, then the reader or the viewer can be forgiven for thinking that there are actually 2 sets of movies and they're for some reason different. Right, so the same amount of space has been kept between bars. Now, were this vertical axis numerical, then we are just forced by the number line to make certain decisions, and we'll be doing that at some length. That's a dreadful pun, I'm sorry. We will be doing that for quite some time on Monday. But what I'd like you to notice is the things that you take for granted are actually decisions that have been made by graphic designers. And when you make your own graphs, you should be conscious of how your decisions affect your viewers. Okay, so what I want to do now is I want to plot a bar chart, this same categorical variable, but I just want to plot the millions. Okay. Okay, so there's actually a discussion. Yes, Torren, it's called a number formatter. It's in the, you look at the optional section of last lecture. You can put in, you can put in, the method is called set format and the option is number formatter. That is not something we require in Data 8, but it's possible. Okay, so there is actually a discussion to be had about how many variables are represented here. Clearly, there are at least 2. There is the categorical variable, which is the name of the movie. And there is the quantitative variable, which is the unadjusted amount in millions that it grossed. But there is a hidden third variable because somebody made a choice for ordering these movies. And how did, how was that choice made? No, we know how the choice was made. It's the same choice that was made here. How was the choice made? Sorted by millions adjusted. It was sorted by this column, but what we're plotting is this column. So we have the title column sorted by the millions adjusted column, and we are plotting the millions column. So there are actually 3 variables involved in this. The adjustment was measuring all dollars in all the different years in 2016 dollars, adjusting for inflation. Yes, thank you, Mokht. Okay, so what I'm going to show you now is what happens when I try something else. So I am going to make a reduced table. It's going to have only 3. It's going to have the title. It is going to have millions and millions adjusted. All right, so I'm using dot select. And I am going to use my call, but only with the categorical variable label. And look what I get. I get an overlaid bar chart. So you see both. Okay, we're going to be about to be kicked off, but you see both variables. And there is the only thing that remains is a question, how do you generate this chart? And the last thing is, how do you generate this chart? So try it out yourself. How to generate this chart. It's from the same data set, and then the answer is there. And I will see you on Monday.